Alright, so in this presentation I'm going to go over the basics of thermal boundaries, condition space in a building, look at the difference between a building shell and a building envelope, discuss the implications for the second law of thermodynamics on heat flow in a building, and then we'll look at R value and U value and how they're related and how that relates to heat transfer. Okay. So a thermal envelope or thermal boundary, depending on who you ask, is the area of a building that encloses the condition space. The condition space is the area of a building that is actively heated and cooled and otherwise controlled. So you can control the moisture and so forth. So you think of like the areas of a building, anywhere that you actively heat or cool on, you sort of like purposely try to control the temperature and all the other conditions. That's your condition space. And that's the unconditioned space is the areas that are not controlled. Okay. And then this image is a pretty good one that shows you sort of the basic in pink is your thermal boundary, right? So everything inside of there we're trying to control. You can see there's a little crawl space or an attic up here that has unconditioned space in the top. In this case, the basement is inside the thermal envelope, which means you're actively heating and cooling that. You have some sort of some sort of room next to a porch. So that's all inside the conditioned space. So all of this area is your thermal boundary. Okay, so that's an important term to keep in mind. That's in the thermal boundary is really the same as the building envelope. So again, it depends on sort of who you ask. The building shell, on the other hand, that separates inside the house from outside the house. So they actually can be slightly different, and I'll show you an example here in a minute. Actually, right now. In this image here, I want you to think which surfaces are the envelope and which surfaces are the building shell. Okay. So let's start with the shell. So the shell, remember, separates inside from outside. So basically, the shell is going to be your roof and your walls and your foundation over here, the floor over here. This is kind of like an in-between space, so I would consider that outside the house, really. So this is all the outside of the house. Okay, so that's your building shell. The building envelope, on the other hand, now the big difference here is this attic looks like it's unconditioned, which means your envelope separates the attic from the main part of the house. This would probably actually, the basement would technically, when you do, most energy auditors would consider that inside the thermal envelope, just because there's exposed ductwork in there. But if that's really well insulated, then you could kind of say it's outside, in which case this is probably your envelope. Okay, so you can see it doesn't always coincide, but it does coincide in certain areas, right? And so you think of some of the building shell materials, plywood, OSB, brick, concrete, some of the stuff we've gone over in terms of building construction from last week. Envelope is mostly going to be your insulation plus all the stuff that's in the shell, right? So if this normal stick platform construction, you're going to have some drywall here, you're going to have some insulation, you're going to have some framing, then you're going to have some sheathing on the outside, maybe OSB. All of that's part of the envelope. Okay, that's all part of the envelope. But really, only the OSB is your building shell, because that's what's actually on bordering the outside of the house. Okay, so all this kind of ties together, right? So we went over building construction last week, and this week we're kind of putting the pieces together a little more. We're adding insulation as well. So that's your basic building shell, building envelope. Second law of thermodynamics. Technically, it is the entropy of the universe always increases, which just means the disorder of the universe is always increasing. You don't need to know that, okay? So that's just kind of a little background information. For our purposes, there's two really important aspects of this. Number one, when you convert energy from one form to another, you always are going to lose some of that to heat and other inefficiencies, okay? So you can't convert something. There's no such thing as a 100% efficient furnace, for example, because you can't. It's impossible, physically impossible, to have a car engine that's 100% efficient at converting gasoline to your mechanical motion. So that's part of the second law. And then the other really important part is that it's not possible for heat to flow from areas of colder to warm without additional heat. So for thing to remember, really, really important, so you want to write this down, is that heat always travels from warmer to colder areas unless energy is added to the system from the outside. So if you have two surfaces, right, so if I have like a hot cup of tea and like my hand's colder and I put my hand against the teacup, the heat is always going to go from the teacup to my hand. Whatever's warmer, it's going to go from that area to the colder area, unless you somehow force it to go in the other direction, which in terms of conduction you really can't do, but there's ways to do it with other types of heat transfer like convection and advection and so forth. And so when you have this situation here, you have a house, this is obviously in the heating season, so 70 degrees inside, 10 degrees outside. I have a delta T. Delta T is a really important term, and that just means difference in temperature. Okay, so I have a delta T of 60 in this, really easy to remember, 60 degree difference. Here's my summer, 70 inside, 90 outside. So you can see the temperature is the same indoor year round. In the summer you have a delta T of 20. In the winter you have a delta T in the other direction of 60. Okay, and so in both of these situations, heat is going to flow from the warmer areas to the colder areas. Okay, so it's going to go from warmer to colder. And the higher the delta, the more the heat is going to sort of want to escape the building. So in your situation on the left, where your delta is 3 times as high as your delta on the right, all else being equal, this heat is going to flow from from inside to outside 3 times faster than it will in this situation, flowing from outside to inside. Okay, so the two important things to remember here: heat is going from the warmer area to the colder area, colder area. So it just depends on the time of day, time of year, that the direction of the heat flow. And the second thing is, the bigger the delta, the faster it's going to flow, all else being equal. Okay, and so heat in a building, one of the main ways that heat flows into and out of a building is through the surfaces, right? So the walls, the roof, the foundation, whatever. And again, heat will always flow from outside, from the warmer to the colder, from the warmer to the colder. So if it's colder inside than it is outside, that heat is going to flow from the outside to the inside. You just can't. There's nothing you can do about that. Okay, that's the direction it's going to want to flow. If it's a lot warmer inside than it is outside, the heat is going to try to flow outside. And again, that's just the second law in action, and there's nothing you can do about it. Okay, and so the the ability of a surface to transmit heat is actually really essential to consider the material that the envelope and the building shell is made of. And that's because of conductivity, or K value. Okay, you don't need to know all the details of these conductivities, but you just need to understand the concept. So aluminum has a conductivity of 1400. It's this BTU inches per hour per square foot per degree Fahrenheit. So what that means, if you take a square inch, an inch thick slab of aluminum, that's 1 square foot. Okay, so imagine like 1 square foot, and there's a 1 degree temperature difference on either side of that piece of aluminum. Okay, so 1 square foot, 1 inch thick, and 1 degree difference on each side. Over the course of 1 hour, you're going to lose 1400 BTUs through the aluminum from the warmer side to the colder side. Now that's assuming that you maintain that 1 degree temperature difference the whole time. So if it's a 1 degree different on either side for an entire hour, you're going to lose 1400 BTUs. You don't need to know that number, but think about this. The difference between that and wood, for example, is 1.6, right? So wood has a conductivity of 1.6. So you take aluminum, 1 square foot of aluminum, 1 inch thick, over the course of 1 hour, you're going to lose 1400 BTUs with a 1 degree delta T. With wood, you take a same square foot, 1 inch thick, same exact size, 1 degree temperature difference, for 1 hour, you're only going to lose 1.6 BTUs. So think about what that means. I'm losing aluminum is about 1,000 times as conductive as wood. So think about house framing, for example. You can make steel, so not aluminum so much, but steel. So if you look at steel framing, 310 versus 1.6 for wood, right? So that's, what is that, 20 times as much? So the point is that if you have different materials, the heat will conduct through them at different rates, all else being equal. And you can see like air is a really poor conductor. That's why insulation works so well, because insulation is mostly air pockets. Rubber is a good insulator, glass wool, and so forth. Okay, so that's your conductivity. So different materials conduct heat at different rates. And this is sort of a false color image, but this on the right is a real thermal image. So that's an infrared camera. So you can see it's definitely cold outside. We're at minus 15 Celsius, and then for the dark areas, and then you can see the purple is a little bit warmer, and the orange is warmer yet, and then the warmest areas are in the yellow. So here's the warmest areas outside, and this is a view from outside of the house, right? So here, and I want you to think about what that is. Go ahead and press pause and think about it. So those stripes, that's the framing, right? And so what that's showing is it's cold outside, right? So it's really cold outside, and that's why it's so cold. This is probably snow, I don't know, right? So it's really cold outside, and you have this house, and you can see that these pinkish purple areas, that's where your insulation is, right? So from the outside, those pinkish purple areas where it's insulated, it's actually a little colder, right? So here's your temperature scale on the right. You can see that these areas are colder than the framing. So the framing is warm, is what's happening here. And I want you to think about how that relates to conductivity. So the framing is more conductive of heat than the insulation is. And so what it's doing is it's conducting the heat, the warm inside of the building. Okay, presumably it's pretty warm inside the building, and that heat is conducting more through the framing than it is through the insulation. That phenomenon is known as thermal bridging, which is when heat, basically, you think of a bridge, a thermal bridge, right? Like a bridge for your heat, so to speak. So you have warm inside or outside, depending on the time of year, and so the heat, the framing, and other things like doorknobs provide this sort of bridge for the heat to travel from inside to outside. All right, so that's a really important consideration, and one of the things you really want to try to prevent with good insulation. So if you watch any of those advanced framing videos from prior weeks, one of the things that things like the structural insulated panels and insulated concrete forms try to do is try to prevent thermal bridging, and that's because this is what happens. You're conducting heat through the building framing, and that relates very closely to R value and U value. So U value is very closely related to conductivity. So U value is how many BTUs will flow through a 1 square foot slab of material over the course of 1 hour when there's a 1 degree temperature difference. So it's almost exactly the same as conductivity, except it's not always an inch thick, right? It's still 1 square foot, still 1 BTU of difference, it's still 1 hour. But in this case, you can have however many, you could have 18 inches of insulation and look at the R value, or excuse me, the U value of that, right? So it's not just 1 inch thick. And then R value is a measure of the thermal resistance. So R value is kind of, frankly speaking, a made-up value, but it's a lot easier to remember. And here's why we use R value. The bigger the R, the better the insulation. Really easy to remember, right? Whereas with the U, because that's transmittance, that means you want a really small U. So it's hard to really wrap your mind around, like small U means really good, where if you tell a homeowner, look, you have R10 in your attic, you need to add R30, and that's going to give you R40. Like, it's really easy to sort of understand, like, R40 is 4 times R10. Really easy to remember. So that's really why we use R. It's also because we can add R's together, but we cannot add U's. Right, so the R is, they're related mathematically. R is the inverse of U, and U is the inverse of R. And we'll go over some of this. So this is really important. R values can be added. So if I have R11 insulation on top of R38 insulation, you get R49. Really easy to remember. Okay, and insulation, really, the R value is primarily a function of slowing down convection and conduction. Convection and conduction. So that whole heat transfer process, insulation slows it down. And that's because it's filled with air pockets. So the U value is how much heat. U value is what we use to calculate heat loss, and we'll do this in a future video. But so U value is how much heat in BTUs flows through 1 square foot of material each hour when there's a 1 degree delta, or delta T of 1. So if you take square foot of whatever it is, and then, depending how the R value depends on how thick that layer is. Okay, so 1 square foot, and then there's just a 1 degree temperature difference on either side. The U value is how many BTUs will flow through that surface in 1 hour. So let me go through an example I think will help explain this. So if I have 1 square foot with a delta T of 1, assuming we have a U value of 1, okay? Wood has about a U value of 1. So I have a U of 1, okay? So I have 1 square foot, 1 degree temperature difference for 1 hour. How many BTUs am I going to lose? 1 BTU, right? So that's what it means. A U factor of 1 means over the course of 1 hour, if you have 1 square foot, you'll lose 1 BTU with a 1 degree temperature difference, and that's exactly what we have, okay? So let's say we have the same wood, but it's 100 square feet. It's a delta T of 1, and it's over the course of 1 hour, right? So same situation, but instead of 1 square foot, we have 100 square feet. So we're just going to lose 100 BTUs, right? 100 BTUs, because it's 100 square feet. What if I have 100 square feet, and there's a 10 degree temperature difference for 1 hour? It's going to be 1,000 BTUs. What if I have 100 square feet, a 10 degree temperature difference over 10 hours? I'm going to lose 10,000 BTUs. Okay, so you can see what happens here is that heat transmission is going to increase, all else being equal. It's going to increase if you increase the U, if you increase the area, if you increase the amount of time, and if you increase the delta T. And I think, try not to get sort of confused by all this. It actually makes perfect sense, right? So if I'm going to increase the surface area, of course I'm going to lose more heat. There's more opportunity for heat loss. If it's going to be, you're going to have that temperature difference for a longer period of time, more heat's going to flow through, right? Makes sense. And then if you think you have a higher delta, it just kind of makes intuitive sense. Like, if it's really hot on one side and like really cold on the other, it's going to flow a lot faster than if it's like pretty cool on one side and just a little bit colder on the other, right? So you increase the delta T, you increase the surface area, increase the amount of time. Increasing the U, that's not as intuitive, but that's something you just sort of have to deal with. That's how it works. So a higher U is worse. Okay, and we try to control all of those in terms of building efficiency, right? And the relationship between U and R is that they're the inverse of each other. So R is 1 over U, and U is 1 over R. Super important to remember, you can add R, you cannot add U. And I'll demonstrate this here. So if I have the following layers, what are their R and U values? Okay, so let's figure out what they are. So we have 3 layers on top of each other: R1, R2.5, and R3.5. So what's the total R? Pretty easy. You add them up, you get R7, right? 1 plus 2.5 plus 3.5 is R7. Super easy. You can add, remember, you can add R's. Okay? So if I want to get the U factor for that, I just take 1 over 7. Okay? R is 1 over U, U is 1 over R. So my U factor, if I have these 3 surfaces stacked on top of each other, R1, R2.5, R3.5, the U factor is going to be 0.143. Okay. So what happens if I convert these to U values first, and then I try to add the U's? I want to demonstrate this, why you cannot add U's together. Okay. So we have R1, R2.5, and R3.5. So to find the U for each of those, very easy, just 1 divided by each of those, right? So 1 divided by 1, 1 divided by 2.5, which is 0.4, 1 divided by 3.5, which is 0.286. Okay, so that would be the U values of these surfaces individually. So let's add those up and see what we get. So we get U of 1.69. So let's look. This is the right answer, 0.143. This is the answer we get if we add the U values. It's 10 times higher than the right answer. That's just a demonstration of why you cannot add U's. It's going to give you the wrong answer pretty much every time. Okay, it's not always going to be 10 times the answer, but it will give you the wrong answer every time. Okay, so very, very important. Remember that you can add R's, you cannot add U's, and then that they are the inverse of each other. And again, remember that heat transmission is driven entirely by delta T, right? So bigger delta, bigger surface area, more time, bigger U, you're going to have more heat transfer. Okay? And, okay, so again, we went over the difference between the thermal boundary, the building envelope, and the building shell. We looked at the difference between conditioned and unconditioned space, the implications of the second law of thermodynamics, and then we looked at how heat is transmitted through a surface, and then how U values and R values are related.